Do I have to do something? Mirror or extend?
I'm not a Mac person.
That's cool. I can just get on Zoom if that's easier. Am I not?
You can just, I think if you just do it on Zoom.
Just do it on Zoom? Okay.
Switch back.
Okay. Share. I don't have my slides, though. What's going on with that? Oh, there we go. Good. Okay, sorry about the delay. All right, it's wonderful to be here and to follow up on the wonderful talks that we've had earlier in the session, talking about what we've learned from these high redshift observations with JWST about the physics of galaxy formation. So as Brant already emphasized this morning, perhaps the most surprising thing about the observations of the number densities of bright galaxies with JWST is not simply that there are so many of them, but that if you look at the number density over cosmic time, going back further and further into the past, for the bright galaxies especially, this has almost not changed at all, right, since redshift 14, even down to redshift of 8 or so, while the number density of dark matter halos, as shown in the plot that Brant showed, is dropping like a stone, right? So clearly, if there was a fixed relationship between halo mass and UV luminosity, then we would see a much more rapid decline in the number of these bright galaxies, which is not what we're seeing. So, as Pablo already mentioned briefly, there have been a very large number of theory papers since these galaxies were discovered, suggesting different possible solutions to this puzzle. And I divide these into two basic categories. So one kind of solution is to just make the galaxies brighter. So you could do that perhaps by ejecting their dust, by making the IMF top heavy, by making some UV light with an accreting black hole, or by making star formation bursty, so brightening them temporarily through short bursts of star formation. The second category is to make stars more efficiently, as, for example, in Abishai's feedback-free starburst picture. So, as in the last talk, we're going to be using the Santa Cruz semi-analytic modeling framework, which was born here in Santa Cruz in collaboration with Joel and Sandy, and I think is well suited to give us insights into this problem because, as Aaron alluded to, the dynamic range needed to understand the statistical populations of galaxies is actually quite large. So this is very difficult to do with a numerical simulation. So I'm going to be focusing mostly on the second class of solutions, on the efficiency of star formation and how it perhaps changed over cosmic time. And I'd like to sort of break this down into two kinds of physical processes. And this is the way that we model things in semi-analytic models. So we have a recipe for computing the fraction of gas that has cooled and flowed into the ISM that is eligible to make stars, okay, that's dense enough and cold enough to make stars. And then that cold, dense gas has some efficiency or some time scale with which it turns into stars, right? And this is something we can calibrate empirically in the nearby universe where we can observe gas masses and star formation rate densities, the so-called Kennicott-Schmidt relation that we all know and love. Then on more global scales, we have supernova-driven winds that can drive gas out of the ISM, perhaps even out of the CGM, obviously making it ineligible for star formation. And the overall star formation efficiency is sort of a combination of these two processes happening on what I'm calling sort of local or cloud scales and global or or galaxy scales. So you already saw a version of this diagram. This is sort of an expanded version here of what you saw from Aaron. So this is the rest frame UV luminosity function at a bunch of different redshifts, where the gray points are a compilation of the observations. And the purple and blue lines are the models that we published. Actually, these are more or less the same models that we published in 2008. Okay, so they really haven't changed very much. And with the improved modeling of photometry that Aaron talked about, these do pretty well at matching the UV luminosity functions out to redshift 12, and then they start to drop below the observations. So what if we just completely turned off that second mode of feedback? So the galaxy scale wins. We don't allow any gas to be ejected from galaxies. We would get the green lines, and you can see that, yes, that does increase the number of bright galaxies at high redshifts, but it also greatly increases the number of low-mass galaxies. We all know this, right? The potential wells are shallower. It's much easier for supernovae to drive gas out. So I would argue that simply switching this wind mode of feedback off is probably not going to solve the problem. Now, what might be different about galaxies at these very early times? Well, as Martin Rees, suggested earlier today, the universe was much denser at these early times. So on the left, you can see observed star formation rate densities of galaxies at high redshift, 5 to 14, can be orders of magnitude higher than galaxies in the nearby universe. And if we just take a dark matter halo of a fixed mass that we've defined in the usual way, right, 200 times the background density of the universe, we would also expect the density of the gas, if it traces the density of the halo, to be several orders of magnitude higher in the past, where we're observing these galaxies with JWST. So what are the implications of that? Before I get to the implications, I want to mention sort of a cute related thing, and that is the sizes of these high redshift galaxies, which we've already heard a bit about from Yuichi and others. So the points here are some observations of the size, the radius, and the UV luminosity of galaxies at redshift 9 to 13. And it turns out that if you just do an abundance matching exercise, so you paint UV luminosities on your halos such that you match the UV luminosity function of galaxies, and then you ask, how big does the galaxy need to be relative to the halo virial radius to match the observations? Okay, this is sometimes called structural abundance matching. Andre Kravtsov and others, including myself, have done this at lower redshift. If you do that, you find that the galaxy size has to be twice the spin parameter of the halo times r vir. In the local universe, this number is 0.5. So for some weird reason, and I'm not saying that this is a causal relationship in any way. I'm just saying it's a curiosity that this seems to match the sizes of these high redshift galaxies. So in the SAM that I'm about to tell you about, we just assume this, and we get a distribution of sizes, including the dispersion in size at fixed UV luminosity, that matches the observations fairly well, based on the rather small samples that we have. Okay, so galaxies are much denser. Presumably the gas, the star-forming gas, is also denser. What might the implications of that be? That's what we explored in this paper in collaboration with Aaron, several of the postdocs in and around CCA, Lachlan Lancaster, Sean Menon, Laura Somovigo, and also with Steve Finkelstein. And what really inspired this paper was work by Sham and Lachlan and others, where they simulate individual star-forming clouds, sort of GMC-sized clouds, 10 to the 4, 10 to the 5 solar masses, including a variety of physics, including radiative processes, stellar winds, etc. I think Sham is going to talk more about these kinds of simulations in a few days. And so what has emerged from these simulations is that if we ask, what is this sort of cloud scale efficiency of turning gas into stars? So what fraction of the initial gas turns into stars before the cloud is dispersed and blown apart by its own stars, right? By the stellar winds, radiation pressure, etc., before the first supernova even goes off. Okay? And we know that in the local universe, that this efficiency is very low, a few percent, right? And that's what's indicated by this gray box, which indicates the range of surface densities of GMCs in the local universe and the observed efficiencies, less than 10%, which also is similar to what comes out of the simulations, which are shown by the symbols. However, as you increase the surface density of these clouds, it's harder and harder for the energy and momentum emitted by the stars to blow them apart. And so they end up converting up to 80 to 90% of their gas into stars over their lifetime. So again, many authors in the past have proposed a very simple analytic model to explain this result that comes out of simulations, and that is basically just an Eddington argument, right? So if you just ask how much momentum is needed to unbind the gas in a given gravitational potential well, you get a critical surface density, and then you can express this efficiency in terms of that critical surface density. So if you know P dot over M, which is just the rate of momentum deposition by the stars, the massive stars, then you can compute this number, and that's the blue line. So without any tuning, that very simple analytic model reproduces the results of these cloud scale simulations very well. So now, in order to implement this in our SAM, we have a size for the galaxy, so we know the surface density of the galaxy. We need to assume something about how the density of the clouds trace the overall density of the galaxy, or the ISM, that's this parameter C. And then we need to assume something about what fraction of the ISM is in these dense clouds, these dense star-forming clouds. So that's another parameter that we called F-dense. Then we also need to know the lifetime of the clouds, the time that they have to convert their gas into stars at this efficiency. And from the simulations, it turns out that the denser clouds also take longer to be dispersed in units of their freefall time. Okay, so even though that time scale in mega years is shorter because their freefall times are shorter for the denser clouds, in terms of the freefall time, their lifetimes are also longer, which partially explains why they are more efficient at converting gas into stars, because they have more freefall times to do it in. So now with those ingredients, we can put this into our SAM to compute the total star formation rate of the galaxy as a function of surface density. And now we can get predictions for UV luminosity functions at these various different redshifts. So this is a horribly messy plot. Let me try to pick it apart for you. The blue line is our pre-launch model, the Kennecott-Schmidt model. So you can think of this as sort of the vanilla model with a Kennecott-Schmidt relation that doesn't evolve with time. The different colored reddish lines, red family lines, are this new, what we call density modulated star formation efficiency model with different values of this parameter F-dense. Okay? So the lowest, darkest lines have F-dense of 0.1, which Andy tells me is reasonable. And the highest lines have F-dense of 1, which is probably an upper limit. So the first thing we learned from this is no single value of F-dense. If F-dense is unchanging over this time period, we cannot reproduce all the observations. Okay, we either overproduce or underproduce the observations at one of the redshifts. So that was interesting. However, it's clear that you can get a lot more bright galaxies with this density modulated model because the densities are so much higher at early times. The yellow line is, again, if I switch the winds off, and so this is probably an upper limit. This is F-dense of 1 and no winds. So that's meant to be sort of a bracketing case. Now, to relate this to what Aaron was talking about, I wanted to show you the efficiencies required to match the observations that came from the toy model that Aaron presented. So that's this gray line. So this is an efficiency defined as the star formation rate divided by the baryon fraction times the halo growth rate. Okay, so the same quantity that Aaron was showing. And you can see that you need efficiencies that are much higher than the blue line, our old fiducial model, and actually towards the F-dense of 1 results as you go up to these higher redshifts. So this again is showing basically the evolution in the star formation efficiency is not strong enough, even when we include this additional effect of star formation efficiency increasing with increasing density. Another promising result is that we're making more stars earlier, right? And so there was previously tension between the pre-launch models and these stellar mass functions that have been reported. Similarly, galaxies that have been observed at redshift 4 and 5 have been found through sort of fossil evidence to have a lot of stars that formed very early. So this model does form stars earlier, presumably relaxing some of those tensions. Okay, all of what I just showed you, and I should have emphasized this more, as I was showing it to you, assume there is no dust. Assume that all of the UV light is being observed. We know that that's not the case. So you might be wondering, what about dust? If Doug Lynn were here, he would certainly be asking that. And so we have implemented a model suggested by Andrea Ferrara and collaborators where the dust can be ejected when a critical density is exceeded. So again, basically an Eddington argument saying that if the radiation pressure is enough to overcome the gravitational potential well, you eject the dust and the galaxy becomes transparent. So we basically took Andrea's model out of the box and implemented it in our semi-analytic models. And it's very hard to see in this plot, so I'm going to go to the next plot. So here the lighter lines are the same models you saw before without dust, and then the darker lines are the models with this dust modeling. And you can see that at low redshifts, galaxies are not able to eject their dust, and so you get a fairly significant depletion of the observable UV bright galaxies. But as you go to higher and higher redshifts, the galaxies are able to eject their dust. There's almost no difference between the light line and the solid line. So this definitely will make the evolution of bright galaxies appear shallower, right? Because they're getting dustier and dustier as you go to later and later times. The other effect that's been discussed in the literature is that, and for which there is observational evidence, is that galaxies may have bursty star formation histories. So we also considered a model suggested by Jelly and collaborators based on work by Jason Sun with the fire simulations. So what they did was to take the fire zoom-in simulations and ask, how large are the excursions in UV luminosity just due to this bursty star formation? So you can think of this as sort of a sigma, a dispersion in UV luminosity at fixed halo mass. That's shown by this plot. And lower mass galaxies are more bursty. They have larger excursions. That's, again, because the potential wells are shallower, and so the bursts have sort of a larger effect on the overall luminosities of the galaxies. So we, again, just took this straight out of their paper and implemented it in our semi-analytic model. And so now we have dust and bursts. And what I want you to look at is the red lines, which have both the dust and the bursts. And what you can see is that because the scale of star formation is shifting into lower and lower mass halos at earlier times, this also boosts the number of bright galaxies preferentially at high redshift. Probably not enough by itself to solve the tension, but it does systematically boost star formation at higher redshift. So to sum up here, I wanted to show you sort of a summary plot of the number density of galaxies as a function of redshift for a brighter limit and a fainter limit. And this shows the effects of adding the dust, which brings down the lower redshift number density of galaxies. The density modulated star formation efficiency elevates the number of bright galaxies preferentially at higher redshift, and the halo mass dependent starbursts also boost things more at higher redshift. So you end up with this flatter behavior in better agreement with the observations. Okay, Martin is standing up. So
that means you have a 1 minute.
I will just briefly say that I like this picture a lot because I think that it makes predictions for other kinds of observations. And that is always a good theory, right? That makes predictions for things you have not yet tested. So the picture here is that a lot of star formation in these early galaxies is happening in these dense clouds of gas, rather massive clouds of gas. You might even think of them as protoclusters, right? And so that may have implications for how galaxies look, for chemical abundance ratios of galaxies, and I think particularly exciting, perhaps for models for how the first black holes were seeded, as we discussed a bit earlier this morning. So let me actually skip over this and just as a teaser show you a simulation that's being run currently by Christian Partman, in which we have very high resolution, 9 solar mass resolution, sub-parsec resolution, star formation with individual stars. And one thing that's particularly exciting is that we couple to a regularized integration scheme called KETCHU to actually solve the orbits of individual stars and stellar remnants and follow the formation of black holes in these protostellar clusters. And so you can see what the galaxy looks like in these simulations. We form these very, very dense star clusters. And so this may be what the earliest galaxies in the universe looked like. So thank you very much. I'll stop there.
Well, that was a really interesting talk, and I, for one, would love to ask lots of questions.
I know, but I used all my time.
Your time, yes.
That's
okay,
right.
Okay, so, Vadim, next speaker.
I'm here all week.
Well, while our next speaker is getting set up, we'll take a question from somebody. Right? Okay.